What lesson are we on? We're on 7.2f. And 7.2f is all about inverse trig integrals. So let's start with this screen where it says, do you remember the derivatives of arcsine, the derivative of tan inverse, and the derivative of secant inverse? We have worked with those earlier. So we take that structure, and now what we're going to do is try to integrate off of this structure. And hopefully you can recognize that, oh yeah, that structure looks like secant inverse. Or if there's no square root and there's adding going on, you know, think tan inverse. So here are the integrals, and where there was a number, like here, that's what we're going to call our a. So this will represent a squared, the number minus the function squared. If I have that scenario, then that should play out like an arcsine of u over a. And you notice on the side, maybe you'll even want to write that down, where a is some constant and u is a function written in terms of x. And for arcsecant, we get that square root. The function comes prior to the constant. There is still subtraction like there was in arcsine, and there will be a u out front as well, or a function of x out front of the square root. If I do not have a square root and I have a squared plus u squared in my denominator, then I'm going to think of arctan, and its formula is 1 over a arctan u over a. So notice the commonality, they're all u over a. For arcsecant, we've got to be careful with that domain, so it needs to be an absolute value of u. Arcsine does not have the 1 over a, but the other two do. So enough said on that. Let's try some problems. So when I look at a, I see a number minus the function. So in my head, I'm thinking a squared minus u squared, square rooted. And that would draw me to thinking that this is going to be an arcsine one. I still would set up that I know that a is 3 in this case, and u is x, then du is exactly equivalent to dx. This is where it could change up. So definitely take and analyze whether you have anything going on between the dx du sub. So all I'm going to do is pop in things. Dx gets substituted for du. I've got the square root of a squared minus u squared. That is prime candidate for arcsine. This will be the arcsine of u over a. U was x, a was 3, and then plus c. Nice easy one to get us started. They really don't get too rough with these on the AP exam. If you can recognize patterns, you're going to be doing great. Okay, I recognize pattern. I have an a squared plus a u squared, and that's going to be an arctan, isn't it? That's going to be tan inverse or arctan if you wish to write it that way. Now, my a would be square root 5. My u squared is 4x squared. Let's take the square root. We're at 2x. And then du equals 2dx. Here's what I'm talking about. We have just plain dx, so I need a 1/2 du to equal dx. Now, let's set up, before I jump into that, let's set this by substituting. So I have a 1/2 du checking in for the dx over an a squared plus a u squared. That is perfect arctan business. And arctan is 1 over a, and my a is root 5. Arctan, or tan inverse of u, my u is 2x over the a of root 5. And I suppose I could write this as 1 over 2 square root 5. I am not going to rationalize that, but realize that if we had to, we could. if it were like a multiple choice and it was, you know, rationalized. Okay, these really aren't so bad, are they? Okay, C really feels like an arcsecant. Do you agree? We have the function minus the constant. That's what happens, function minus constant in an arcsecant. So I'm thinking arcsecant in my head. I know that this is my u squared minus my a squared. And I know this is going to turn out to be very nice. du is equivalent to dx. A turns out to be 3. And I'm going to have 1 over a arcsecant or secant inverse of u over a. Absolute value u, so let's keep that x positive, over a plus c. For D, ooh, this looks interesting, doesn't it? Very interesting. Sine inverse of x, and then I get the square root. Okay, this is not any of these forms. However, the bottom does look like arc sine, doesn't it? What do you think we should use on D? I'm thinking this is just a typical U sub. And here's why. If I let my u equal sine inverse x, sine inverse x, then du is equal to u prime, so 1 over square root 1 minus u squared, and my u is x, so there we go. And then the derivative of x is dx. And that is what I'm seeing here. So I'm just going to split this apart to make it more obvious, in case you're kind of wondering where I came up with this. This here was our du substitution, and then the u was equal to sine inverse. Now when I integrate this, I'm going to have 1/2 u squared plus c, and let's plug in for u. U is sine inverse x quantity squared plus c. So yeah, just watch. Things can take a turn. What do you think this looks like? To me, I'm seeing function minus constant. I'm seeing u squared minus a squared. And that leads me to believe I'm in arcsecant mode. So now let's set up. Our u squared is 25x squared. That means u is 5x. Our a squared equals 1, so a is 1. And I'm going to do my substitution. So, du equals 5dx. I almost missed this. Then I have 1/5 du equals dx. Now I'm going to do my substitution. Maybe I'll go up high. Okay, so dx, oh, there shouldn't be 2 dx's. Ignore that one. 1/5 du replaces dx. I have the square root. 25x squared is our u squared. 1 is a squared. So far it's looking fine. What I don't have is just an x. How can I get an x? I can play off of this and solve for x. So that would mean x is equal to 1/5 u. Okay, so now I'm going to replace my x, with 1/5 u. Dividing by a fraction is like multiplying by its reciprocal. And I'm left with something that looks like this. Those cancel. And we get 1 over a arcsecant or secant inverse of absolute value u over a, which is 1, plus c. Okay, I can clean that up. Secant inverse absolute value of 5x plus c. That should be our answer. All right, moving forward. Example number 2 is not, while it kind of looks like arctan, what about this going on top? If I said this is u squared, I'd end up with u squared over a squared plus u squared, and that is not an arctan pattern. So what I do notice is I have degrees that are equal. And anytime that happens, or if the numerator is larger, or numerator degree is larger than denominator degree, I should use a technique called long division, because it means that our denominator will go into our numerator and we can get things simplified. Okay, so let's use long division. Get rid of all my markings there. So I'm going to have x squared inside, x squared plus 1. I would prefer it mixed that way, so I'm going to rearrange that. Now it's all about the large degree into the largest degree. X squared goes into x squared one time. Okay, that was pretty easy. X squared plus 1 is going to get subtracted. Remember, you got to come and multiply, distribute that 1 through both of them. And I'm going to have x squared minus x squared, and then nothing minus 1 gives me -1, which is a remainder. So I get minus 1 over x squared plus 1. Write it as a remainder. So now what I've just done is found that x squared over 1 plus x squared dx is equivalent to 1 minus 1 over x squared plus 1 dx. Right? We just used division and it still stays equivalent. What I would want to do with this is break this into 2 integrals. And integrating the first one would be an x plus c. I'm going to hold off on the c and just put one big c out at the end. I can see that this is standard arctan u over a, u being x, a being 1. So it's going to be that, and this would have been a 1 over 1. So I don't really need to write that. I'd have x minus tan inverse of x plus c. It doesn't take very long, and we can get some quite difficult integrals. And you just have to be, alert to all your possibilities. So far we know u sub, we know some trig substitution techniques, we have arc inverse, arc trig inverse integrals, and now the technique of long division. Another technique that comes into play is completing the square. If you remember when you completed the square in Algebra 2, you took your middle term, divided it by 2, squared it, and it kind of became the fill-in for us to create a perfect square trinomial. And then I'd have my plus c, and I'm going to back off exactly what I introduced to complete the square. So things stay balanced between here. This is a net 0 position. This will turn out to be what? An x plus b over 2 quantity squared plus c minus b squared over c squared, whatever that number adjusts to now. So knowing that, I look at this problem and I think, well, definitely u sub doesn't work because I would need something in terms of x. I need the derivative of this polynomial to be present, and it's not. It doesn't look like it's a trig substitution. It doesn't look like it's any of the inverse trig integrals either. So let's complete the square and see where that takes us. So I'm going to have dx x squared plus 12x plus 12 divided by 2 equals 6, and then we'd square it. So plus 36, and then I've got the plus 37, and I'm going to back off the 36. So here's the two numbers that I'm introducing, netting out to 0. And you're like, well, how is that helpful? Well, let's see what the next step does when we simplify. We would have a perfect square trinomial right here. Perfect square trinomial. Oops, get the spelling right. Nomial. And that factors into x plus 6 quantity squared. 37 minus 6 is a plus 1. Aha! Do you see what I see? I'm thinking this is arctan. This is my u squared. This is my a squared. So I get u squared plus a squared. Arctan. So if u is equal to x plus 6, du is equal to dx. Okay, nice, perfect substitution. We know that a is 1. So in our head, we're going to say it's 1 over a arctan u was x plus 6 over a plus c. And now obviously I don't need the ones. And there's our answer. So sometimes this completing the square can become an arctan. Very cool. That leaves you with the homework that looks like this. You should have a worksheet in your packet. Have a good day.